Assalamualaikum warahmatullahi wabarakatuh. So welcome to chapter 5, integration, and in this chapter you will be looking at three subtopics. The first one is fundamental theorem of calculus, indefinite integrals, and techniques in integration. So we're going to start off with the first subtopic, which is the fundamental theorem of calculus. Well, as briefly mentioned in the chapter 1, there is a connection between two branches of calculus. So the first branch is differential calculus and the second one is integral calculus. So differential calculus arose from the tangent problem, whereas the integral calculus arose from the area problem. So to illustrate what is the idea of area problem, which you are going to see in this chapter, here is the figure of a curve. So this is the curve. This is the given by function fx. So the interest would be to find what is the area under the curve from 0 to 2. So this is the area of the curve. Now, in order to estimate the area of the curve, what we can do is we can actually go on and construct some rectangles, okay, a number of rectangles. So for example, if you have the original interval from 0 to 2, you can divide this interval into equal sub-intervals. So this is the first interval, the second interval, third interval, and fourth interval. So they are divided equally, and based on that you can construct a rectangle according to this point here. So you can construct the rectangle, and based on this rectangle we can find the area, because we know that if you have a rectangle, the area of a rectangle is just multiplying the length and the width. So you can find what is the area of this first rectangle, what is the area of the second rectangle, the third rectangle, and the fourth rectangle. And then you are going to add up A1 plus A2 plus A3 plus A4, and you will get the estimation of the area under the curve. So that's the idea. Now, if you refine the construction of the rectangles, if you make it smaller, if you construct more rectangles, then the approximation will get better. For example, in this figure here, the interval from 0 to 2 is divided equally into 8 intervals. So here is the first one, second, third, fourth, fifth, sixth, seventh, and 8th. And based on that, you can construct 8 rectangles. And you can see that you will get better result with that. What you can do is, again, you repeat the process of finding the first area, the second, the third, and so on. So this is area for the 8 rectangle, and you can find the area under the curve by adding up A1 plus A2 until A8. So of course, if you construct a rectangle that is smaller and smaller, the approximation will get better, because then you will get to really choose the height of the rectangle according to the curve. So you can do it more better with more rectangles. Okay, so you will be able to get better results. So that's the idea. So as you can see here, when for example, when the number of rectangles is 50, the result is 3.33320. And if you make the number of rectangles as large as possible, that means n approaches infinity, then the area will be 3.33333. So this is the area under the curve that you are looking for. Okay, so this guy here, Isaac Barrow, discovered that differentiation and integration are just inverse processes. Okay, now we are going to formalize the idea that I have explained here in this slide, where you can mathematically define or write down the formula to find the area. So as I said earlier, our area can be found by adding up the area of the first rectangle plus the area of the second rectangle and the area of the nth rectangle. So you can construct as many rectangles as you would like to. So and again, a rectangle can be found by multiplying the length and the width. So if you look at this figure here, the length is this one. So for example, this represents the length fx1 star. So notice that this is the curve given by fx. So if you, for example, choose point x1 star, so let's say this is the point in the middle here is x1 star. So by substituting x1 star into the function, this is the result that you will get. So this gives you the estimation of the length. So this is the length times with delta x. Delta x is the width. So this is delta x. This one is delta x. And delta x is just x1 minus x0, for example. Recall you have seen the idea of delta x. This is just taking the difference of x1 minus x0 or x2 minus x1 and so on. So delta x represents the width. Okay, so and it is the same value because the width should be equal. So delta x. Now for the second rectangle, it will be x2 star. So for example, this is the point of in the middle, we choose x2 star. So if you substitute x2 star into this function, it will give this result here. So this estimates the length of the rectangle, and you multiply with the width, which is delta x. Now similarly, if you have, for example, this one, this could be delta x4 star. So if you substitute into this function, the answer will be given as such. So this estimate the length of the rectangle, for example. So you will be able to find the area of the fourth rectangle. And again, the process is adding up the first rectangle, the second rectangle, the area of the first rectangle, the area of the second rectangle, until the area of the last rectangle. And again, because you are making the number of rectangle goes as big as possible, so this is about implementing the idea of limit. So when the number of rectangle goes to infinity, when you make the number of rectangles as many as possible, then you'll be able to get the area under the curve. Okay, so the process of writing a1 plus a2 plus blah 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 plus an can be written more compactly by using the notation of sigma. So sigma here represents the summing process here. So if you have a1 plus a2 blah 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 plus an, that can be represented as ai. I equals to 1 until n. So this process, so whenever you see this is the process of a1 plus a2 blah 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 plus an. So this is just the way of writing a long expression and making it looks more compact. So let me just erase this. So now what we have here is a long expression. So this is a long expression, and you can make it more compact by writing it in this manner, because this is the process of summing. So this is the summing process, fx1 star times with delta x plus so on and so forth. So this one can be written using this summing notation. So this is the summing notation, sigma. So sigma I equals to 1 until n. So whenever you see this expression, this is basically meaning that you are going to replace I equals to 1 into this notation. So for example, this is going to be f x1 delta x star plus, you're going to continue for I equals to 2, so that will be x2 star delta x, and you're going to continue this process until I equals to n. So you have f xn star delta x. So that's the process. Okay, so basically this is the long expression which can be written compactly using the sigma notation. Okay, next. Now, the equation that you have seen in the previous page, which is this one. So this is the equation. This is about finding the area. Okay, this is what you have seen in the previous page. Brings us to the definition of a definite integral. Okay, so this is the definition. So if f is a continuous function defined for a certain interval, so the interval is between a and b, so x is between a and b, where the interval AB can be divided into n subintervals with equal width. So how to divide the interval into equal width? You have b minus a over n. So this is to construct as many subintervals as possible so that you can construct many rectangles. So delta x here. Now, suppose the sample points x1 star, x2 star, blah, blah, blah are chosen in these subintervals, then the definite integral of f from a to b is given by this. Well, basically it is saying that if I want to find the area, I don't need to go on with this process of adding up the areas. Instead, I can just use integration. So I can use this process. So this is the integration process. I will calculate an integral of that function. So fx is a function from a to b. So the limits are from a to b. Okay, so that's the idea. Now the integral sign. So this is the integral sign. This is introduced by Leibniz. It looks like elongated s. It is elongated s. So this is s, but you elongate it. So it represents the limit of sums, because the idea of finding the area is based on summing up the rectangles. Okay, so they are talking about the limit of sum, so they use this its sign here. This is elongated s. And lower limit and upper limit are represented by a and b. So this is the lower limit and this is the upper limit. And when you talk about integration, it is actually the procedure of calculating an integral. Alright, that's all for now. So I'll see you in the next video with some properties about definite integral. Thank you very much for watching.